So we're continuing on now, and we are now uh, working to build upon what we learned in 1.1.2. And this is about how to do vector addition and how to use vector addition and all of the equations of motion. So if you probably remember from your books, if you've done the reading, there are 4 equations of motion. Well, where do those come from, right? And those come from, well, we'll learn, come from merging together the position versus time graph and velocity versus time graph equations and merging those two together, and also representing those equations in terms of vectors. Okay, so we're going to just build on this, what we learned last time. Okay, so if you haven't done so, please do the reading and begin your homeworks. Well, let's review real quick what is vector addition, right? So if you have a velocity vector, if you have an a vector pointed up and to the right, so if you have a positive a vector pointed up and to the right, and you have a positive b vector pointing down and to the right, and you add those two up, that means you're going to be matching the tip of one to the head of the other. So I'm going to be matching the tail of b to the head of a. Then the resultant vector is the addition of those two vectors. Okay. So you're going to match those tip to tail. So you're going to this is almost like the hypotenuse. This is the hypotenuse, and the hypotenuse is the addition of those two vectors. Okay. And so if you walked up and to the right, and then you walked down and to the right, then that ultimately means that your resultant, you started here and you ended here. And that's what the resultant vector is, and that's the addition of those two vectors, A and B. With subtraction, if you have a positive A vector pointed up and to the right, and you have a positive B vector pointed down and to the right, and you need to subtract B from A, then you need to reverse that positive B vector, so that instead of pointing down and to the right, it'll be pointing up and to the left, and that's now the negative B vector. And then add those two together, so you'll take the head of A and point it to the tail of B, and then the resultant vector would be, you started here, you walked up and to the right, then walked up and to the left. That means you started here and you ended here, and that's the resultant vector, which will be up and to the right. Okay? And so that is vector subtraction. Okay? Well, let's practice that, but let's do that in one dimension. Here we have one of your tutorials, and we have 2 examples from your tutorials, okay? So what we have is, we have, and I don't want you to get mixed up with left is positive and right is negative, okay? These vectors, whatever direction that they're shown, just use it as being a positive vector. So this is going to be positive A, which is going to be 1, 2, 3, 4, 5, 6 units to in that direction. Positive B is shown to be to the left, and that will be 1, 2, 3, 4 to the left. Okay, so here you're just supposed to add these two things together. Okay, so to get the C vector, you're going to be adding the A vector to the B vector. So that means you go positive 6 to the right, and you go so if we're going to take this as positive 6 to the right, and we're going to add to that, we got to do tip to tail, we're going to add to that 4 to the left, and that means the resultant vector is going to be positive 2 to the right. So this is what they're looking for, okay? So it looks a little bit weird, but whenever you have a vector pointing in a direction, you could call it that is positive for that direction. And so it's weird. In this case, they wanted a C vector, which is the addition of both of these vectors. And in a way, you could even interpret this, not the way that Mark wanted you. Mark Summers is the person who created this. You could actually say this. that this b vector is actually -4, right? So that b vector is -4. So you're adding to that +6 a -4, which is going to result in a +2. And that has to be the c vector because they're asking you to perform these operations. Okay, so this is what they're looking for. Okay, so over here you have a b vector that is 1, 2, 3, 4, 5, 6 to the left. So this is the positive b vector that's 6 to the left, and then the a vector is going to be a +2 to the right. Okay, well, what they want is they're wanting to get what is the c vector. So you have to get the one unknown vector here. So here you have to find out what the c vector is, and to get c, you have to subtract b from a. That means your b vector, which is positive, which is pointing to the right, pointing to the left, is now going to be pointing to the right at a +6. And then you're going to add to that the a vector, which is +2. So that means your c vector is going to be something this long, because +6 +2 is going to be c, which is going to be +8. So this is what you're supposed to do, and this is the basics of vector tutorial. And all you're supposed to learn from that is to adding two vectors tip to tail, okay, and then go ahead and solve for an unknown, okay. So I want you to go ahead and complete this tutorial before you move on, okay, and it'll help you do practice, okay, and use this video as your reference. So moving on, you could actually apply this to what we have just learned. Okay, so another part of this this tutorial is we have you could be categorizing things as speeding up and slowing down in constant velocity. Okay, so what we had learned before is that if your velocity vector and acceleration vector, in this case they're going to be both pointed to the left. Okay, if you have both of those guys pointed to the left, then that means that definition is speeding up. You could speeding up, slowing down, constant velocity, or turning around. And which direction would that be going? Well, it'd be moving to the left and also speeding up to the left. So this would be a straight line. So what I want you to do is try to get as far as you can in this lecture tutorial, and you're going to categorize these as speeding up, slowing down, constant velocity, or turning around here, and straight line, turning clockwise, turning counterclockwise here. Okay, and if you've got those two categorizations, then you should draw the velocity vectors and accelerations here. So there's quite a few you could get done there. All right, so we know that we've seen a position versus time graph, right? And now position versus time graphs are going to have a curve to them, okay? And so we've seen this as a curve fit for the position versus time graph. Oops. Plus initial velocity times t plus 1/2 at squared. And we also know on a velocity versus time graph that something like this would look like this curve fit, okay? That would be v final equals v initial plus at, right? Well, by merging these two equations together, okay, so if I solve, typically when you merge two equations together and you want to eliminate a variable, you take the more simple equation and solve it for the variable that you want to eliminate. In this case, we want to get in a prediction equation for speeding up, slowing down type of motion, some type of accelerated motion, but without using the acceleration vector. So we're going to take this equation and solve it for A. And when you do that, you get V final minus V initial over T. Well, now you're going to plug this into for this A here. And when you do that, you get this evaluation, and then you do a bunch of algebraic steps, and what you get is V final equals, X final equals X initial plus V final plus 1/2 V final plus 8 V initial times T. So overall, what you get, and this is probably how it's shown in your book, is V final plus V initial divided by 2 times delta T. And so we're doing this so that we could actually get an equation of motion to solve for position or time or velocities, okay, without using acceleration, okay, because sometimes in problems you're not given an acceleration vector, although they are saying it's speeding up, but they want you to solve for the total displacement of the object in this case. But they give you the initial velocity, they give you the final velocity, and tell you the total time change, and they want to find what the displacement is. And you would think to try to get acceleration to do that, but you don't need to. Okay. And here is another type of problem again, but in this case, what we want is we don't want to use time. We want to show accelerated motion, or we have an acceleration motion kind of going on. So again, you have the same kind of curve fit, and you have the same velocity versus time linear fit. But here we want to solve for final velocity, for example, but without using time, and we have an accelerated type of motion. So again, we're going to use the most simple equation and solve it for the one variable that we want to eliminate. And then we're going to go ahead and plug that into here. And this is a lot more algebra, as you can see, but overall what we get is this type of equation. And the way it's probably presented in your books is this, V final squared plus V initial squared plus 2A times the displacement. Okay, so you probably see this as one of your additional equations of motion on top of the curve fit for a position versus time graph and a linear fit for the position versus time graph. So overall, here are all the different types of equations of motion. And I just added, by the way, I just added this here just to let you know average velocity, just in case. But you don't necessarily need this. But overall, here we have the linear fit of a position versus time. We have the linear fit for position versus time graph. For a velocity versus time graph. And we have the curve fit for a position versus time graph right here. So this is a position versus time graph curve fit. And this is the velocity versus time graph linear fit. And so this comes out of the merger of both of those, as I showed you. And this other equation of motion comes out as a merger of both of those. Okay? So we're going to need to keep these four equations of motion in mind. And this, I'm going to call this as 1, this is 2, this is 3, and this is 4. As we move into the next activities for this, for adding velocity vectors, adding initial velocity vector to final velocity vector, and also displacement vectors and acceleration vectors, and using them to solve for these equations of motion. Okay? So, but before we do that, let's move on to the next slide and talk about something. Okay? So the linear acceleration, what linear acceleration is it's because velocity is a vector, velocity can change in two ways. Okay, I want to talk about turning in a circle. Okay, if you are moving, so if you've ever done a donut in a car, and I'm not talking about eating donuts in the car because that's awesome, but I'm talking about taking your car and just doing a full circle. if you've ever done that for fun, don't do it. Just not recommending doing it, but let's just say you're turning to the right. Okay, so you're doing a full circle as you're turning to the right. So here's the center of that circle. And here, if you'll notice, if you look at your speedometer, it's saying that you're traveling at a constant 5 miles an hour as you're turning counterclockwise. Okay. So if you're going slow and you're doing turns for fun, you'll notice that you're traveling really at a constant speed. Okay. And but it's weird. You feel if you're turning like this and you're in the driver's seat, well, if you're in any of the seats of the car, you're going to feel the right side of that seat belt digging into your right side, which means something is pulling you in towards the center of the circle. And this is a case where you are moving at a constant velocity, but you're going to always be accelerating towards the center of the circle at each one of these points in time. Okay, and so it's weird. Velocity, so acceleration can happen in two ways. Acceleration can happen in a way that if your velocity vector is increasing in size over time, and if that's true, then that means an acceleration vector had to be added to your initial velocity vector to equal your final velocity vector. But also, in this case, your velocity vector's direction is changing over time. And as long as, now I'm not saying your speed is changing, you have a constant speed of 5 miles an hour, but here you're moving to the top of the page, here you're moving to the left of the page, here you're moving to the bottom of the page, here you're moving to the right of the page. But the actual speed is the same every time. However, there is an acceleration vector associated with this. And that is another way that velocity can change, that acceleration can change, in that the direction of your initial velocity vector, you add to that an acceleration vector, okay, and now you have a final velocity vector, okay? So that means you would be moving up and to the right initially, and then you have a final velocity vector that is going to be up and to the right. That means you had to have an acceleration vector being added to your initial velocity vector to be equal to the final velocity vector. Okay? So that's another way motion can change, is that if you're just simply, if you look at it, you're just simply changing the direction of your velocity vector, okay, by adding an acceleration vector to it, and that creates a final velocity vector, and that changes your initial velocity. So that's a change in your velocity. It's changing the direction of your velocity. Okay? So we're going to be taking these tools that we learned about vector addition and also those 4 equations of motion that we learned. And we're going to be using vector addition to create those equations of motion. So for example, and we've seen this before, if we have an initial velocity vector, and we add to that a final velocity vector, okay? So we have your final velocity vector, and we add to that a negative initial velocity vector. Well, that is a change in your velocity vector, and that change in your velocity vector is your acceleration vector, either in the negative or in the positive. Here, if you have an initial velocity vector and you add to that an acceleration vector, then you have your final velocity vector. So in this case, this is your change in your velocity vector, which is actually your acceleration vector. Okay. So also a part of that one worksheet that we were doing, 1.1.3, we had some problems where we're given, in this case, we're given a displacement vector, delta r, and we're given an initial velocity vector, and we actually have to find the final velocity vector and the acceleration vector, okay? So let's do it. Here we have an initial velocity vector that is 2 units to the right. And I'll say that there's no rules. I'll just say just each block is 2 meters. and it takes 1 second. Okay. Well, we know your entire displacement vector is going to be 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be plus 2 meters over the period of a second, plus 2 meters over the period of a second, and your displacement vector is positive 8 meters. Okay, so what you do is I'm going to lay out the displacement vector on top of this, okay, which is 1, 2, 3, 4, 5, 6, 7, 8. So the displacement vector is on top of this. Well, just by using logic, okay, that means our final velocity vector has to, if your displacement starts here at 0 meters and it ends here at 8 meters away, and your initial velocity vector is only 2 of that, then that means your final velocity vector has to be the other 6. Okay. Well, that kind of makes sense. And the cool part is, so now that we have our final velocity vector, we could actually estimate the size of our acceleration vector. That means if we have an initial velocity vector of plus 2 and we have a final velocity vector of 6, that means just by, if you think about it, that means acceleration had to add 4 to this number over that 1 second to make it become positive 6. Okay. To make it become positive 6. So you could use this as a way to just kind of think about it, but also if you want to use the equations of motion, here's another way of doing it, right? So you're given delta r and you're given the initial velocity. Well, here's our equation of motion right here. And we're going to try to relate delta r. So delta r in this case, r is, we're going to call it delta x in relation to these equations. And delta x is x final minus x initial. It's minus those positions. Okay? So here we have this. So we're going to use this equation to help us. We're actually going to use number 3 to actually help us resolve the difference of how to use delta x and initial velocity to get final velocity. All right. So delta x here, I'm going to just rewrite this equation, is equal to initial velocity plus final velocity over 2 times the change in time. That's what this number 3 equation is. So we're going to now go back to our little problem right here. So if we can change this to here, I'm going to write the equation that we had. Delta x is going to be equal to initial velocity plus final velocity over 2 times delta t. Okay, and I want to point out that this is 0 seconds, and now it's at 1 second, and this is 2 seconds. So our time, our delta t, is going to be this delta x, or rather this delta r in our case, is over the period of 0 seconds to 2 seconds if this takes place from 0 seconds to 1 second mark, right? That's the definition of initial velocity, right? So we need to manipulate this equation to be equal to the final equation. So what I'm going to do is I'm going to multiply both. I'm going to multiply delta r times 2, and I'm going to use this in a different color to make it easier to recognize. Okay, so delta r, it's not showing up too well. Let's use blue. Delta r times 2 over t. Okay, multiply both sides by 2. divided both sides by t is going to be equal to v initial plus v final. So 2 delta r over t is going to be equal, well, actually minus the initial velocity vector is equal to the final velocity vector. So in this case, our delta r is going to be 8 meters, and the total delta t that we're multiplying on both sides is going to be 2 seconds, right? Because 2 seconds minus 1 second, so that's going to cancel out. And we're going to be minusing off that an initial velocity vector, which in our case is going to be 2, it's going to be a positive 2 meters per second, but we're subtracting that off, and that's going to be final velocity. So this is going to work out to be 8 meters per second minus 2 meters per second, and that's equal to the final velocity, which is going to then be 6 meters per second is the final velocity. Well, that's what we got right here. All right. And the cool thing about that is once we have this, we could then get the acceleration, okay? Okay, to get the acceleration now, we have v final equals v initial plus a delta t, okay? Well, now we have v final, so I'm going to solve this for a. I'm going to have v final minus v initial divided by delta t is going to be equal to the acceleration. Well, v final we know is 6 meters per second. V initial is positive 2 meters per second. And that's going to be divided by the total time, which is 2 seconds minus 1 second. Well, that acceleration vector is going to be 6 minus 2. So that's going to be 4 meters per second. But that acceleration vector happened from 2 to 1 second, right? From 1 second to the 2 second mark here. Actually, let me use a different color hat. So that acceleration vector was added at the 1 second mark to the 2 second mark. So, so this is going to be 2 seconds minus 1 second, which then is going to be 4 meters per second squared, or 4 meters per second squared to the right. And so that's why we got this. So this is what you're supposed to do, is use, basically what I want you to do is use whatever method you can to figure out the size of those vectors, and then use those vector equations, and they're only going to be from the 0 seconds, 1 second, 2 second mark to actually solve these equations. So you're supposed to be practicing everything that you're going to do, and you're going to want to use all 4 equations of motion to do this, okay? So in the next section, we're going to be moving on acceleration, accelerated motion, speeding up, slowing down type of motion, but in the context of position versus time graph, velocity versus time graphs, okay? And so we're going to be adding that as a layer of detail, okay? So hopefully you've learned about vector addition and using displacement vectors, acceleration vectors, velocity vector, initial velocity vector, final velocity vector, to actually integrate that into the 4 equations of motion now that we're going to be using. Okay? All right, bye.